So what we're going to do today, we're going to go through Tensorflow. We're going to have a little look about how Tensorflow works. We're going to start off with some basic understanding about deep neural network models. Then we'll look at the architecture of Tensorflow, and then we're going to move on to Cloud ML to actually examine how we can start doing this in production. So without further ado, some of you that attended the last talk probably already saw this slide. I was walking past and I saw the yellow, so I'm sorry for using the same slide if you've already seen it once today. But I want to just basically ask, can you put your hands up in the audience if you're already doing something on machine learning? Okay, keep your oh, don't put them down yet. So can you keep your hands up if you're doing something with deep neural networks? And keep your hands up if you're using TensorFlow already. Okay, so we got like 4 or 5 people. I'm sorry to you guys. You can help me out if I get stuck. For the rest of you, what I'm going to do first is basically go through an understanding of a deep neural network. That's one of the things that you might want to do with TensorFlow, which is really good at. So the basics. This is taken from a code lab which we provide, which is available on our site. So there will be a slide in a moment which you can all take photos of with a link and everything. But we're going to look at a problem, and that's minced, recognizing handwritten digits. And we're going to look at how we could do that in the most simple way. So we're not going to go for the fully convolutional, to make like the 99% accuracy. We're going to look at the basic neural network that we could make to actually give us an understanding how neural networks work. So the first thing that we're going to do, we've got 2 layers here. So we have the input layer and we have the output layer. So this is a pretty simple neural network. It would be rude to call it a deep neural network. And basically what we're doing, those images, those handwritten images that we were looking at, they are all, let's say, 28 by 28 pixels. So if you stretch them out into a long vector, you get 784 pixels. And what we're going to try to do is use those 784 pixels. We're going to map them to each one of our neurons. We're going to get an output, and we're going to try and predict which number it is. So the only information we really have is about the color, the grayscale of each one of those pixels coming in. So ignore the function here for the moment. We'll come back to that in a moment. So the first thing I want to emphasize is this X and W here. So those pixels that we just looked at coming in, there are 2 things that neuron's going to do. It's going to do the weight, and it's going to do the input. And the weight is basically, this is the thing that makes the whole neural network learn. We're going to emphasize or give less attention to that weight if we find that feature is significant. So when we're looking at one of those neurons, sorry for flickering back and forward now, all of those inputs are coming into each neuron, and we will have a matrix of weights which corresponds. And the first thing we would do is a weighted sum. So we would take the value from the pixel, so let's say we'll put it on a scale of 0 to 255 or decimal, whatever you want, and we would take a weight, we'll multiply those 2, and we'll add them all up for each one of those neurons. There's an extra thing here called the bias. That bias is basically, if you think about it, if you go back to maths class, you had like a y-axis and an x-axis. The bias is just basically where it intercepts on the y-axis. So we'll leave that for now, but that's what it does. Okay, so in the previous slide, what I showed here is the Softmax function. The Softmax function, we will come back to in a little bit, but because we don't have multiple layers in our network, we want to do some activation, but at the same time, we want to work out probability. So Softmax has these nice properties. It will actually take our scores, like that value of that weighted sum, and turn it into a probability for us. If we were to add more layers, which is what we're going to do here, and this is, well, as it states, it's overkill. It's not how you should tackle this problem, but just to give you an understanding of how you could tackle this problem. What we're doing now is adding more layers to our neural network. So the idea of deep, having multiple layers comes into play. And in each one of these layers, we're going to do the same thing. We're going to take the value, the input, we're going to add a weight, we're going to do that multiplication, and we're going to sum them up, and we'll pass it through to the next one, and so on and so forth. Inside each of those neurons, we are going to have an activation function. One function that you might use is sigmoid. Lights just changed. Okay. what does an activation function do? What's it all about? So let's have a look at here. At the top row here, these are all the different kinds of, like, let's say the common activation function. The most common activation function, let's say the most easy activation function, not the least and the most common, but the most easy is identity. You know, what you put in, you get out. So you put in 10, you get it back 10. You put in minus 10, you get back 10. If we look at sigmoid, so it's basically mapping it in between space of 0 to 1, and it's kind of saying, well, actually we're going to squash it a bit, no? So values at the tail end or at the front, they're actually going to kind of get to the same value, and the stuff that's in the middle, we're going to kind of emphasize a bit more. That's closer to that identity. A lot of neural networks actually use sigmoid. What we've actually found with imaging is ReLU, which is this function here, which is almost the same as identity, except for anything that's negative, we're just going to put to 0. It's a function that works quite well in that space. There's the reason why that one works well, so how it was explained to me, it was explained to me that if you look at sigmoid, that's how we kind of interpreted the world, but when they started to look at some of the biological functions of eye cells and this kind of stuff, they saw that the signal that was actually coming through was more akin to this. So they thought, well, let's give it a try. And they did. And it seems to work quite well in images. And you can obviously think for the features that you're trying to get, you're not losing, or you're not kind of, let's say, making that information at the front end all flat anymore. So you're not bringing it all into the same space. So you're not losing that emphasis. I think the better explanation I heard was they tried it, it seemed to work well, and that was a good to go further. The Softmax function at the bottom, basically, this is a function that's going to allow us to take our scores or our logits, and we're going to do something to actually turn that into probabilities. So this is a good function to have at the end to use in a classification space. So we've got our scores, which is the top row, and we've got our scores, which is the bottom row. I'm going to say this around the wrong way again, aren't I? Yeah, we have our scores, which is the bottom row, and what we want to compare it to is what the actual values are. But the actual value in this case is a handwritten digit, so it's anywhere between 0 and 9. So we want to compare those, so we're going to do something called one-hot encoding. So there's basically a 6 becomes a load of zeros and a 1, and then a few zeros. A 5, well, you can imagine. You can just look at this and you can see, right, so 9 is going to be 0, 0, 0, and then 1 at the end, and 0 is going to be 1 on a tail end of 9s. And then what we can do is actually take the actual value, and we can take our probabilities, and we can work out the distance between those two. In neural networks, a popular function is cross-entropy. What cross-entropy is basically looking at is how much noise or how much information is there between the actual value and what we predicted. We want to minimize that. Another function that you might have heard in this space that you might want to use is like the sum of squared errors. Just a different function, which kind of works better in this space. So it's a trial and error to work out what's good to apply. So what you're going to do is, if you can imagine that let's say we predicted a 6, and we look at the distance between 6 and the 0.9 and the 1, that distance is 0.1, but we would do that for all of the things that we predicted it might have been. And if those distances are bigger, well, that's going to add up, or it's going to multiply out, and it's going to be a worse prediction. The last part of this, so if you imagine, we've actually gone through now like the whole forward pass. So basically what we've done, we've taken input, we've multiplied it by some weights, we've done our activations, and then we've come to this function where we calculated the loss or the amount of information that's left over. Now we need to go and basically train our network and make it better. So we need to go and work out what those weights should be. How we do that is backward propagation, and the function, and basically it's a descent algorithm, gradient descent. So if you imagine all of those features mapped in space, and what we're trying to do is work out what is the optimum. Now, we have this nice property with a gradient, it goes down, so it has gradient descent. So we're trying to find out what the global minimum is, where we have the best fit. And we will basically retrain that network over and over again to work out what the best set of weights are, and that will become our neural network. So this was super fast, because the rest of the talk I'm going to explain on architecture and how to actually start getting this stuff into production. This slide here, you can go to the GitHub link there. You can also go to the link here on Google, and you can find this whole tutorial, and you can walk through it and have a go. And each of those steps are explained. The mathematics behind it is explained a little bit more as well. So if that's what you find most interesting and you want to get out from this, that's a place I would recommend to start. So, machine learning. What makes successful machine learning? It's going to be fun with a fan in a moment. So successful machine learning. I mean, as Tino said in the keynote this morning, these things have been around for a long time. Why are we hearing so much about it in the last years? It comes down to storage and computational power. So in that space, you know, we want to have lots of data, we need lots of storage. We want to be able to actually process this data, because if we're going to be doing all these multiplications and everything with lots and lots of data and complicated networks, there's going to be, you know, a lot of passes involved. So yeah, we need to have computational power to actually work through our good models. The good model part is something I've had a few discussions with today even, and the kind of just like, okay, what is this democratizing AI all about? What is it exactly we're trying to do in that space? Well, put your hand up. I'm going to keep making people put their hands up. Put your hand up if you use Linux. Okay, that's a lot more than the first one. Put your hand up if you actually contributed to the Linux code base. 1, 2, right, we have a chat later. Very interested to know what you've done. Right, so my point here is, everyone's using Linux, everyone's building this stuff on top of Linux, yet out of this whole audience here, there are 2 people in the audience that actually contributed to Linux itself. In the same way, I think we can start looking at machine learning. That's the space we're moving into. There are a lot of people that spend a lot of time you know, studying maths, studying machine learning to actually give us the tools that we need to be able to do this stuff. But what we're seeing now is more and more people using it, and more people bringing it, helping to bring it to production. So our thinking along democratizing AI is to basically bring that into the same space. Make sure that everyone can, at some level, start using machine learning, can start interacting with machine learning. It's going to become, I mean, these are the predictions. You're already seeing it now. We're going to, in a few years' time, we're going to have self-driving cars and, I don't know, telephones that, you know, do everything for us and make us coffee or whatever else that they need to do. So it's going to be like a huge part of our life. I have 2 children, and I don't think my children are going to grow up to become mathematicians. Maybe they will, but judging by what they're doing at the moment, I think the chances are quite higher on something with firefighter and, I don't know, maybe the other one's going to be a chef. They're quite young. So they can explore. But I do want my children, when they grow up and they're in this world, to not feel alienated from what's happening in the world and how the world works. So I think democratizing AI, as my personal opinion, is like extremely important to all of us. So we should all develop some understanding so we can actually understand what everyone else is doing in the world that makes the world work how it works, you know? So that's an important part I wanted to bring across. Let me grab the clicker again. So I just told you what we needed for good machine learning, for it to be successful. These lovely things here are our new pods of TPUs. Each one of these pods is 11.5 petaflops. So that's a whole load of capacity to train models. To give some kind of perspective on that, if we take some of our more difficult machine learning models that we've used for translation and NLP and this kind of stuff, when we retrained them, they would take, you know, days. With these type of ASIC devices in a pod and set up in this scenario, we can actually get that down to hours. So that means that we can really bring, you know, we can, the kind of real-time value to what we're trying to do with machine learning. You know, something's changed in the world, we need to reflect that, we need to retrain our model. Having this power enables us to do that. And cloud is really the only, I mean, the only space where we can actually offer that at scale to everyone. Because if you think about how much money it costs to develop an ASIC device, I don't know the number, but I'm being told that it's lots and lots and lots and lots and lots. You know, that's not something a company is going to go and invest in. But if you want to train your model and actually have it play a part in the real world, you know, when things are changed and reflect those changes, you might want to have access to this kind of capacity. So, as Peter in the previous talk mentioned, we have 2 ways that you can benefit from ML at Google Cloud. One is with the APIs. This is also a good part of democratizing in machine learning as well. There are common problems. There are common capabilities that we're developing more and more of. Being able to share them over open APIs for anyone, any developer to actually implement that in their application, to bring some new feature capability to the application, that's a great thing, whether it's translating something or turning speech into text so you can process something or understanding sentiment. That's all great. And if you're in that level, you know, good luck. It's a really great space to be in, and it will go really fast. If you need to be on the left, which is the building your own models, we have some offerings there as well. So the two parts that are really important here is, one is TensorFlow. It's open source. So if you have ideas, if you're a data scientist, or if you're a distributed computer specialist and you think, I've got ideas how this can be improved, you can contribute to that project. You can collaborate with us on that project, you know? It's not just about Google making something, say, come and use this. It's not ours anymore. It's open source. It belongs to everyone. So come to that space and invite. And what we try to do in Google Cloud, this is true of all of our open source products, is that we provide a managed service. So you can take your TensorFlow model, we're going to look at that in a little while, and you can bring it to the Cloud ML service, and you can train it, and you can host it there, you can serve from there. And if you don't like what it's offering you, you can just take your model and go and do it somewhere else. So, you know, that kind of, I can choose where I'm going to do this. I can choose where I'm going to train. I can choose where I'm going to serve up from. That's what we want from cloud, you know? That's the idea of open cloud. So our job is to make sure that we do the pricing properly, that we offer the best speed, the best performance, that we offer the best security. They're the things that we need to focus on. And you can focus on what that code actually has to do, and we'll provide you a space to run that. So this was the architecture of the video API demo. So for those of you in the last talk, you've seen this quite in depth now. For those of you from the keynote this morning, just to give you a little taste, if you were using those APIs, how simple an architecture would be. This is all serverless. I mean, with the most work that went into this application was up here to actually build what the application should look like. The whole bottom row where the magic's happening, from people uploading their videos to a serverless function, a little JavaScript function that's just basically say, oh, you uploaded a video, run this API. And then the API itself, that's all serverless, and it's really like a few lines of codes, and then you have that capabilities up and running, and you're extracting metadata from your videos. And you can use this pattern for any kind of problem that you might have, where it's turning speech into text or anything else. So let's have a little bit look deeper now into what machine learning is. This, and one of my favorite slides, is this is what people, when you have a chat with them, like think of machine learning. You know, this is our kind of common perception. Tons of data, really difficult maths, and magical results. And especially that part in the middle, that's like, oh, all right, I'm not really good at maths, mate, what's my role in this? This is closer to what's going, well, that was too quick. This is closer to what's going on in machine learning. The big challenges to actually doing machine learning start with collecting data. And that can be a real headache. I'm a data engineer, that's my background. Finding how to collect data, how to start organizing that data, that consumes a lot of time. And if you haven't done that, you don't have any data available for you to go and do your machine learning on. So that's obviously really important. The next part that's really important is creating the model. And then once we've got the model, we need to train it, we need to make sure that it's actually up and running, that it does something useful, and then we can go and deploy the model. This workflow involves a lot of time. And I would say each of those little hexagonals there, they all involve maybe not equal amounts of time, but they all have their own challenges. Today we're not going to focus on the first two, we're going to focus on the latter three. But I'm going to let you see a little architecture now of how we might actually do this in production. So when we're talking with customers, they say, oh, this is the kind of problem I've got, like how could I do this? So the top layer is let's say the input, that's what we basically, when we're going to do the training, and the bottom layer is the predicting, the production part. So there are a few things to notice here. The service that we're going to use for actually collecting data and extracting them are PubSub and Dataflow. So if you're in the big data space and you want to hear, there are talks about that today, or come by the Instant Insights little booth out there and we can have a chat about that, or my colleagues as well can talk to you about how they actually work. In fact, they're doing some machine learning prediction there, so they can really show you that whole pipeline, actually playing live, so you can go and have a look and see what's going on. So basically what we need is capabilities to be able to collect data quickly. Now PubSub can scale to millions of messages per second, or you could have batch processing if you want there. Dataflow itself is Apache Beam, it's an open source project, and Dataflow will allow you to actually do that processing either in streaming or batch in a unified model, so you can kind of treat them the same way. And then if you think about what that means, it means, for example, you could be training on batch and doing all your processing in batch and extracting your features, but when it comes to production, maybe you're getting similar data or the same data, and you've got to apply the same kind of logic. So you could use that same pipeline, now apply it to your streaming pipeline for the predictions that are coming in. And that's exactly what's going on in that demo out there as well. Then we want to train the model. So CloudML offers us a space to train that model. So we can actually go from Dataflow and say, right, no, let's go and train the model now. The data's available, blah, blah, blah. And once we've trained it, we need to serve it. Now CloudML also provides you that place to serve. And we'll look at a little bit more in detail what CloudML does and doesn't do in a moment. So let's move on to TensorFlow and spend a few moments on the architecture of TensorFlow. Just excuse me while I take some water. TensorFlow. Okay, can you still hear me? Yeah, sorry. TensorFlow, it's a system for distributed parallel machine learning. It's general purpose, data flow graphs. There's a lot of words going on there. What does that all mean? And it targets heterogeneous devices. What do we mean by all of those things? Well, first of all, this is a framework. It's hugely popular. It has more than 50,000 styles on GitHub for doing machine learning problems. That's a good space to be in. It's open source, great, and there are lots of people actually using this. So when you go and you need to work with other developers or you need to employ people to help you develop this model, you've got a big community of people that are already using this. So that's really important. What's the data flow graph and what kind of devices? Well, let's go to the data flow graph first of all. So just think of a graph of nodes. There are many systems out there that have graphs of nodes. So this should be a common concept to most people, I would imagine. And basically, we're moving from left to right in this example, and we're going to do, in those nodes in the middle, we're going to do certain operations. So matrix multiplication, adding, activating things, the cross entropy, working out that loss function. So there are some of the things we might do there. So this is, okay, nothing special yet. The next part that's really special, where it starts to get special, is in the name itself, tensors. So if you have a physics background or maybe mathematics, tensors, you already know what they are. It's an n-dimensional array. So why is that special? Well, think about what an n-dimensional array is, first of all. So we start with a scalar, and we move to a vector, and then we have a matrix. It's kind of like a table in a spreadsheet. And then we go on to a tensor of n dimensions. 3 dimensions will provide you a cube. So you might have an extra dimension there, which is something to do with time, for example. Or if you were building a convolutional network, you might have something like different channels of color. So when you're going to do your convolutional steps, and what it basically allows you to do is transfer data from that one node of the graph to the next node and retain the shape of the data. So if you couldn't retain the shape of the data, if you remember in that first example when we were predicting those digits, because we weren't doing anything convolutional, because we weren't trying to take those little samples and actually work out, we lost basically all of the features. So we only had the grayscale ready to tell us what was going on. So how many black pixels were there? How many white pixels were there? How many gray ones? Which of those add up to tell us that this is that digit? But we lost all the kind of like things like the curves or the texture, you know? And obviously if you're processing like more difficult images, that's going to be much more important. So being able to keep that data together as we pass it through those different nodes is really, really important. The next thing is it has state. So we can go and actually update some of those variables within our network, within our, let's call it our flow, and retain the actual value as we move onwards. So we can do things like checkpointing, we can update biases and that kind of stuff. And the last thing is distributed. Wow, that's a bit of a tongue twister, isn't it? It's distributed. I'm going to get better at that. Ask me when I'm off stage to say it again. So basically, we want to say, well, we've got a lot of nodes. We need a lot of computational power. How are we going to split this up? So TensorFlow provides us the architecture to actually go and take those separate pieces of work that we might want to perform on one node or multiple nodes and go and assign them to different machines or different chipsets. So this is kind of the architecture of TensorFlow in one slide. The bottom bit, the distributed execution engine, that's where that magic's all happening with actually, okay, what chipset am I going to take advantage of? So am I going to use CPUs on a single machine? Am I going to use GPUs on a single machine? Am I going to run GPUs on multiple machines? Am I going to have some kind of ASIC device like the TPU, which I just discussed? So all of those things, we want to be able to take advantage of those. So that TensorFlow distributed execution engine does that for us. And then as we move up, we have some front ends, and that's where we start doing our mathematical or our machine learning problems. And basically, we have a number of layers in there. So the first layer, the layers, is where you build models. So the stuff I showed you at the beginning for the mint data set to try and recognize those hand-written digits, that was actually built in layers. And like I said, one of the things about layers is that you're going to spend a lot of time wiring your model together. And then you're going to want to take your model and run it somewhere else on a different architecture, and you're going to need to make some quite fundamental changes to it. So that's a difficult place to be in. It's a lot of work. But maybe you need that. Maybe there's something that we don't provide that really requires that level of... It's also the best place to go and learn stuff. So if you want to understand, and that's why we show it in the other code lab, if you go through a code lab there and you actually do that stuff, you'll really have a good feeling for what a neural network is all about. But in production, in our business, when we're trying to predict things, when we're trying to do regressions or classifications, or we're trying to process images or sound, whatever else, we want to be able to turn this around a bit quicker. We want to be able to take advantage of things quicker. So that's why we have the estimator level. Another popular library which integrates, as you can see, with TensorFlow is Keras. So if you're using Keras and you like Keras, continue. It's a great library. You can take advantage of the back end of TensorFlow to run your models. Our estimator is at that same level, so you can choose things like, okay, I want to do an LSTM, a recurrent network, and these are the things I need, and you start configuring. And if you do it in that layer, you can basically then say to TensorFlow, right, now run it on the single machine, or now let's go and run it in the cloud on multiple machines. So first of all, you don't have to do all the hard wiring, and second of all, you get that distribution and those capabilities back. So that's a really good place to be. But if let's say your problem is a little bit more commonplace, like a regression that you want to do, or a wide and deep network for some recommendation stuff, you think, actually, I don't want to spend my time configuring this network. I want to take advantage of a network that's already out there. I just want to kind of bring my data and see what happens. That's where the canned estimators come into place. So we're really trying to make sure that regardless of the level, even if you're actually building these models, you have these different levels with which you can come in and actually start working. And on the estimator level, it doesn't mean because you're in that level, you can't go and build your own model, or do something that's different that hasn't been done before. You can. We have a custom estimator there, so you can actually take advantage of that custom estimator class and start building your model there, and then use that to run in a distributed fashion as well. So estimators, if you're going to be doing stuff on TensorFlow and you want to do it in production, estimators is a real must. So let's have a look at Cloud ML. So we spoke about TensorFlow, what we're going to do, and now we're going to do some demoing and actually look at how we can get this to production and what that actually means. Because these are most of the questions I get when we're talking to customers, like, okay, I built my model in TensorFlow, how can I now go and run it in the cloud? Well, let's have a look. So I'm just going to move this fan. What we have here is some data, and it's some census data from the US, and we're going to use it to predict income category. What does that mean? We just want to basically know, this is more about the process and how useful the model is, but we want to know if someone's earning more or less than 50,000. And we're going to use Cloud ML for that. So the first thing that we're going to do is we're going to run a model locally. And I'm going to kick that off straight away, because it's going to take some time to run. So I did here the local, I believe. Yep. While this is running, we're actually going to look at what the code is doing again. So what we're doing here, we're using Cloud ML engine. So this is the API from Cloud ML. We've built a model with an estimator. I'm going to show you some code, what it actually looks like. So the important part here, there are two parts when you're creating this. One is the task, what you're actually going to do, and the other part is the model. So the task is the kind of orchestration of that. And as you can see in the model here, I will scroll down a little bit. I want to show you, where are we? That's not good. Let's scroll back up now. Okay, here we go. So I basically want to show you here the actual estimator that we're returning. So this code here, this is where we're actually building our estimator. So you can get a kind of feel, zoomed in enough, you can get a kind of feel for the kind of stuff that you would be doing there. So we're taking layers, we're saying how deep it's going to go, that kind of thing. What type of activation functions we're going to be using. So this is still running. what you're seeing at the moment is that I just installed TensorFlow in a little Python environment here, and I didn't compile TensorFlow. So if I was going to use TensorFlow on my own machine, I could actually compile to take advantage of my hardware. And because I haven't done that, it's just saying, well, you could use any of these hardware, you know? The next thing I'm going to do is launch TensorBoard. Now, TensorBoard is, if you're familiar with like Jupyter notebooks and those kind of things, you might use something like matplotlib to actually kind of graph out and see what's going on. And again, it's like an epiphany moment. So TensorBoard will allow us to do that kind of stuff and much more, but in our distributed system. And so if we're running this in the cloud, we're running it locally, we can actually take advantage and see what's going on. So let's launch that. Log. And I believe the log there is the census output. And I'm going to allow this process. That's not good. And I can actually now come in here and look at how accurate my model is. I can, there's pretty, I can look at, so here's the accuracy. I can start looking at the loss of the model, so you can see that training went, you know, okay, evaluation was pretty poor. But what I can also do is go here and actually, so bearing in mind we've just used an estimator, you might be interested in actually, okay, what's actually going on in that network? What have I actually built? So it will give you the ability to come in here and actually look, and it's going to be super handy when you're actually debugging stuff, to look at how that model is actually constructed and what's going on. So TensorBoard is included in TensorFlow. You can just launch it. And I've just connected it now locally to my, I run that job locally, and I will show you the code for doing that. This is great. What slide am I on now? I should be over here and here. And present again. There we go. So I really wanted to have a look at this API call. G-Cloud, ML engine, we're telling it local, we're going to train this locally. And there are a few things that I'm going to pass in here. So the training data, the evaluation data, and where the model is stored. And as you see, I'm using variables to actually pass that in. And at the moment, I will show you the file and what it looks like so you get a complete feeling for what it's doing. So let's quit this one, and let's do cat on the local. So if you look, I basically exported some variables here, and I've just told it, okay, look, this is my training file. It's a local file, my local system. So you can see what I'm actually passing through. So here's the API call itself. So you get a good feeling for exactly what we're doing in a local situation. Now we want to take that and do something more with it. So we just trained our model in the local environment. Let's now, if I was to continue in the local environment and want to run it distributed, all I need to basically say is that little keyword there and run it distributed. And again, I'm running it in my local environment, in my local machine. So it will take advantage of the hardware that's there, whether it's multiple CPUs and multiple cores or GPUs and that kind of stuff. So that's the important, that step that I told you about, configure, like compiling it to take advantage of your hardware. So when you're setting up TensorFlow. So now you're saying, look, run on my local machine and just take advantage of everything that I've got, everything I can throw at you. Okay, but it's still my laptop, and it's even hotter than I am because of the warmth. So how are we going to run this in the cloud? Well, let's look at a single trainer in the cloud. So basically what I'm doing here, the part I said before, local, that's changed. So now I've got jobs submit. And this is basically telling it, run it in the cloud. Another parameter that I've got here is region. So in which region do I want to run this? You know, do I want to run it in the US? Do I want to run it in Europe? So you can decide with that service where you're going to run it. And again, you provide the training data and evaluation data. But those parameters now, they're not going to point to my local file system. So what are we doing? Well, basically, we take the data, we upload it to Google Cloud Storage, and we just point those parameters now at the Google Cloud Storage. So all you need to do. So the example I'm going to give you is actually, well, the code I'm going to show you is actually how we run this in the distributed training in the cloud. So basically, we have a concept there, and it's called the scale tier, and you can choose at what scale you want to run TensorFlow. So do you want to run this on a distributed system? Do you want to have GPUs? Do you want to have some kind of custom setup? Do you want to have TPUs? They're all different scales that you can configure. You can also configure the worker type, so you've got a lot of flexibility there in actually deciding what resources you're going to throw at this problem that you have. So let's come back here now and have a little look at what that file looks like. So basically, the biggest changes up here is that I'm saying, instead of pointing at my local file system, point at this Google Cloud Storage bucket. That's all I've done. And then down here, instead of running it on local, I'm running that job in the cloud by saying job submit. So you see there's very little change to your code, your call to actually interact with TensorFlow when you're using the Cloud ML API. I'm not going to run that in the cloud now, because obviously what happens when you run something in Cloud ML, it will go and say, basically try and claim resources for you to run that. That will take a few minutes, and then it will start training the data. That will also take the time that's necessary, and then it's going to be available. We've got 8 minutes left, but I am going to show you how to start making predictions on that stuff. So I'm going to show you the code that we need to deploy it, first of all. So we've made a model now. We've trained that model. How do I deploy that model to Google Cloud? So basically, the first thing you have to do is create a model. So this command here would actually, under our Cloud ML service, will create a model for you. And the second command will actually take your version of the model, so the instance of the model, and create a new version. So if you think about what that looks like, let's come over here. So here, under models, I've created a model called Census. The training I just did will actually produce a job, and you see I ran that just a couple of days ago. So that job that I run, that was the last, actually creating that model with my training data. And then basically, I call that second command here to create a new version under that model. So if we go to the models and I click through on Census, you'll see that I actually have multiple versions. If you think about what that means in production, is that you could actually take Cloud ML and use it to train your TensorFlow model, serve it up in production. You can then start working on a better version. Maybe you've got some new data, maybe you've got some insights in the model. Train that, evaluate that, see if that works. Create another version, and then maybe even A/B test that. So you could point your customers in, say, like, go and use that model. Is it working? Is it giving you a good prediction? No? All right, let's keep using the old one. Or if it's working well, we can now switch everyone into the space. So you have this framework that's really going to help you to do stuff in production. And the last thing that we're going to do is make a prediction. And that we are going to do now, so let's have a quick look at prediction. And I'll make a prediction with both models, so with both versions. So, just wait a moment. The silence. The demo gods aren't with me. Oh, here we go. So that's my first one. And my second one should be coming any moment now. I'm going to wait for you. There we go. And we can actually see a difference in probability in those scores there as well. So let's go in and have a little look at that file. And basically what you see is I'm calling the Cloud ML engine to predict, and here's version 1 and there is version 2. Let's change that file for a second. Let's go through and get rid of our version 1, which wasn't so great. And let's run it again. And we should see that come back much quicker. So the first time, I hadn't been using ML for a while, so everything needed to warm up. But once that's in place and you're making your predictions, you can see that that call again now is much more fluid. You're getting it back straight away. Let's go to the last few slides now. So that's how you make a prediction. So we're using that Cloud ML API. We've trained our models, we've deployed our models, we've deployed new versions of it, and we're now using it to make our predictions. So you can kind of see how this site seamlessly integrates with Tensorflow. So you can do all your work in Tensorflow, and now you have this tool to basically do your production pipeline as well, from training all the way up to serving. A few things to mention before. The Cloud ML service has some other properties as well. So one of the things that you can do is hyperparameter tuning. So if you're using an estimator, some of the things that you might want to have as hyperparameters, so these are basically just parameters that you're passing externally to your model. Might be, for example, okay, I'm doing a recurrent network and I want to go so many levels deep. So you might say the number of levels deep is so far. Or you're doing a learning rate, that's kind of like, I showed you that gradient descent when you were trying to actually optimize. And basically on the gradient step, you're taking little steps down to find out where the global minimum is. And if you imagine trying to traverse a valley, if you were taking 2 big steps, you might just jump from side to side. And if you were taking 2 small steps, it would take forever or take a long time. So your learning rate, and you can apply decay to that as well, is saying, right, we'll take a big step and then slightly less, and then like decrease the size of the steps as we see that that change is having less and less effect into our actual funds. There's a way of optimizing that. So all of these things, so to work out what the best learning rate is, to work out how many levels deep we want to create our neural network, these are things, if you're going to go and do this like by yourself, you would have to go and retrain your model and rerun it. So basically hyperparameter tuning is basically say, expose those things as parameters, and then use the service to say, I want to spend so much on my model, so it's like, this is the range, I'm going to go between 2 levels deep and 10, and I'm going to go from a learning rate from this to that. And then you basically say to Cloud ML, go and run this, and you create a configuration file with that configuration, and it will basically try out all those different configurations, and it will come back, and it doesn't just go willy-nilly and try all those things. It will work out, okay, I did this, that doesn't look so good, so maybe if I take a step in this direction, that looks better, let's keep going in that direction. So work out what the best set of parameters are for your model, so you'll get the best working model as well. So the model that trains the fastest, but also the model that has the most predictive power, the most accuracy. So that can really, that's another headache that you have when you're trying to train these things when there's a certain scale. It's because, like, what is the best, especially if you're in this customer level, this custom estimator level, and you're trying to say, what is the best set of configuration? So Cloud ML actually allows you to do that. It will go and do that experimentation for you, and you can decide how much bandwidth you give it or how much money you want to spend to work out. So you can say, this is worth this much to me because I want this accuracy, or it's not. The last thing, but I really don't have time to demo this now, is Cloud Data Lab. There is a talk later this afternoon, I believe, on cloud, and I'm not sure if they're going to show Cloud Data Lab, but one of the things, they're going to show some of the big data tools, and I asked, and I wasn't sure if it's going to show Data Lab or not, but Data Lab is basically a managed Jupyter notebook. If you go to our Cloud Console, and you basically, you can go in there and use Cloud Shell and just do Data Lab, create, and give it a name. It will spin you up an instance. You can give it a machine type as well if you think I need more power than the standard machine type. And basically what you'll get is your own instance of a Jupyter notebook running. It's connected well, it has ungit running on there as well, so you can connect with a GitHub repository, or you can connect with the Git that's actually on the Git repository that's actually included in the cloud project, so you can share that with multiple people across your project. You have a Jupyter notebook, everything's installed there, so like TensorFlow is there, it's up to date, all the stuff you need, so all the kind of good Python libraries that you might be using, but also the integration with tools like BigQuery and Google Cloud Storage are all there. So basically by using Data Lab, you have an environment which you can spin up in like just a few minutes, and it will give you everything you need to actually start building these models and experimenting them within Google Cloud. So that's why I included this slide just as a call out, so you can go and have a look at that if you want to say, how do I get started? Where can I go? And if you do that, the Cloud Data Lab will also give you some folders which connect to our cloud GitHub repositories. And you'll see in there examples on TensorFlow, on the sensor stuff, on running it in the cloud, on running it locally, on creating different types of networks from convolutional to recurrent. So you'll see all these different things there, and you can actually walk through some of those examples. So it's a great place to go and have a look if you actually want to start today. And one more thing. This GitHub repository, so Google Cloud Platform Cloud ML samples, are where all of these samples are actually located. So, just go to GitHub, type Google Cloud Platform. In fact, if you go to Google Cloud Platform, you'll see all our repositories there. So if you go to the ML samples folder, then you will actually see all the ones. And the one I did today that I showed you, so if you actually want to go and see how this works in a bit more depth, is the census. So it's up there. And they give you 2 examples with census as well. They give you an example of estimators, which I just showed you, but they will also give you an example of core, so on that layers level. So if you're like, I really want to see what the difference is in terms of work, you can go there and look at those 2, explore the code, and see how much work you actually save by using the estimators. So I encourage you to do that. I've got 39 seconds and time for half a question. So is there any, really, one question? Go. Yes, you can run Keras if you're with the Cloud ML, yes. How? Come and find me after, and I will give you some links. Okay? You're welcome.